Oh hi, and welcome to this online lecture on this thing that we call 4 vectors. A nice mathematical addition to your understanding of the theory of special relativity. So I'm going to assume that you already know how special relativity works and what Lorentz transforms are and how you can transform the amount of distance and the amount of time from one inertial system to the other. Because in this online lecture I'm not going to add any more physics. The only thing I'm going to do is put the physics understanding that we already have into a new mathematical notation, a mathematical notation of 4 vectors. And this mathematical notation comes somewhat with a learning curve, but it has advantages. And one of them is that it is extremely economic. You don't need to write as much anymore now if you understand 4 vectors. But more importantly, it gives a geometrical interpretation of what we mean by the theory of special relativity. And you can deduce all kinds of new properties of 4 vector special relativity if you understand this language. So even though there's no new physics in what I'm going to tell you, this notation is extremely helpful if you want to understand on a deeper geometrical level what special relativity is. So let's talk about the word 4 vector for a moment. You might be tempted to think that a 4 vector is simply 4 numbers grouped together in a column, because hey, that's what you call a vector, just a couple of numbers grouped into a column, and that's about it, that's a 4 vector. But that is not quite what a 4 vector is. A 4 vector has special properties. I mean, those 4 numbers that you want to group together in a column better have these special properties combined with each other for us to be allowed to call it a 4 vector. There's a definitional matter there. And to understand that definitional matter, I think it's good to look at a 3-dimensional example of what a vector is. So let's create a coordinate system just in normal 3-dimensional space. And if we actually, let's make it 2-dimensional, that makes it even simpler for the point that I want to make. Here's a 2-dimensional space, just the flat space of this whiteboard. And I can take a point P and locate it somewhere in this YZ space. And if you want to know where that point P is, well, you count the amount of steps in the Y direction, that happens to be 4 in my example. You count the amount of steps in the Z direction, that happens to be 2. So that means the point P, its location is given by, in Y direction, that will be here, is 4, and the Z direction is 2. There you go. The location of point P is 4, 2 in YZ space. Here is a couple of numbers turned into a column. Does that make it a vector? Again, you have to be careful. We are tempted to put every block of numbers and put columns around this and call it a vector, but you need special properties. And what is this special property that these numbers have? It's a symmetry. Mathematicians call things symmetries if that means you get to do some operation on your numbers in such a way that sure, the numbers might change, but something about the combination of numbers does not change. That's what you call a symmetry. That's what mathematicians call a symmetry. And mathematicians only call these numbers a vector if they obey one of these particular symmetries. So, what is that symmetry? It's rotation. If I were to take my Y and Z axis and rotate them by a certain amount, in fact, let's do it right now. That is going to be my red axis, the primed axis. Right? I've rotated the system by a certain amount. I don't keep them rotating. They have rotated and then now are stationary again. Well, then the numbers have changed. Because according to my red coordinate system, the point P is not at location 4 anymore. In fact, the point 4 would be here-ish or so. But it's slightly further ahead. Maybe it's 5. Okay, so where is the point P in the primed, the red coordinates? Well, it's not at location Y is 4, it's now at location Y is 5. Okay, so that number has changed. However, the location in z direction has also changed. Because it used to be at location 2, but right now is, I don't know, something that's smaller than 2. It's probably bigger than 1. It's some number. I didn't count it out exactly, but it's a different number. So right now what you see is that once you've rotated your axes, 4 has changed into some different number, 2 has changed into some different number. So things look very different all of a sudden, but here's that symmetry. There's one particular thing that has not changed, and what has not changed is the distance from the origin to the point P. In the blue system, I mean, I can actually put my ruler against it. In the blue system, it's this amount of distance, but so it is in the red amount of distance. The distance from me to the camera is, well, 1.5 meters. If I'm going to rotate by a certain amount, my axes have rotated. Sure, the camera is now at a different XY direction compared to me, but the 1.5 meters has not changed. So there is a symmetry involved. You can rotate these axes as much as you want, but you will, and sure, you will get different y and z values, but you will never, ever, ever get a different distance from the center to the point P. Well, that's a symmetry that we're looking for, that mathematicians require for these numbers to be called a vector. So to put it into mathematics, x squared plus y squared is always the same as x prime squared plus y prime squared. Because no matter if you are in the red system or in the blue system, Pythagoras theorem will always tell you the difference from the center to point P, even though this number is different than that number is different than that, the combination stays the same. And it's exactly that symmetry, the fact that you can rotate yet always end up with the same distance, what allows us to call these vectors. Well, why mathematicians are so fuzzy about these things. So there we go. That's what you call a vector in three-dimensional space. Now let's go to special relativity, because in special relativity you also have combinations of numbers that are the same always. And again, that combination of numbers, sure, the numbers themselves might change, but the combination stays the same. And we already know what those numbers are. The amount of time between two events in the blue system and the red system, if the blue and red system are moving with respect to each other, the amount of time between any two events is not the same in the blue system as it is in the red system, because time dilation and all those kinds of things. The amount of distance between the two events, as seen from the blue and the red system, is also different because of Lorentz contraction and these sorts of things. All good. But, and here's your relativity for you, the total amount of space-time distance stays the same. So what do I mean by space-time distance? Well, if you also take into account the amount of time between the two events, and you also square them, but now you subtract them on both sides. This one. This combination is the same as that combination. And for full completeness, I should also, to make it four-dimensional, I should also add the z distance on both sides. Let me clean up a little here. Minus c dt prime squared plus dx prime squared plus dy prime squared plus dz prime squared. This combination is always the same. It's what we call the Minkowski line element, and again I'm assuming that you are familiar with this statement. So I'm not telling you something you didn't know. I'm simply saying that we now have again, well, numbers in a four-dimensional space, not just x and y, but also x, y, z, and also the amount of time. And yes, if you go from one inertial system to another inertial system, the numbers individually change. dt is not the same as dt primed, and dx is not the same as dx primed, so on and so forth. But this combination is the same as that. And remember, that's enough for a mathematician to take these numbers group them together into a column and call it a vector because they share a symmetry. And the symmetry is not the rotation as we saw in the original two-dimensional space, but it's going to different inertial systems. And that is what defines a 4-vector. A 4-vector is defined as CDT, the amount of time, the amount of space in all three spatial directions, column around this. This is a 4-vector because it obeys, well, that this particular Pythagorean theorem is the same in all coordinate systems. This is a 4-vector. So, what is a 4-vector? Is it just 4 numbers columned? No, it's 4 numbers columned that obey this rule. That's by definition why we call this a 4-vector. So far so good. Now for some notation. A 4-vector we typically write down not as a column with 4 thingies in it, but as only one symbol, dx mu. It's dx with a Greek index on top. That index is not a power. It does not say dx to the power mu. It is a label. Mu tells us which of those 4 numbers we mean. Mu is 0 means the upper part, the time part. dx1 means the x part. dx2 means the y part. dx3 means the z part. So that's what I meant at the beginning, that 4 vectors are economically written. Instead of writing down this full vector, you only have to write down only one symbol, and you, by the labeling by mu, you have 4 of these thingies all in one go. Let's look at how dx mu transforms if you go to a different inertial system. Again, knowing your special relativity, you already know how the dt prime and the dx prime and the dy prime and dz prime look. So let's write those as a 4-vector. So this 4-vector wise will be called dx mu prime now, but we know how this looks. I know how my primed coordinates look in terms of the unprimed coordinates. Those are the Lorentz transforms, right? So let me write it down. CDT primed is the same as a gamma CDT plus or minus, depending on which direction things are moving. Dx, that's the Lorentz transform. That if you know things, well, let me stick to my color code consistently. There you go. Yeah, all good. This is if I know the amount of distance and the amount of space in the unprimed system, the blue system, I know how I can find the ones in the primed system, the red system. And I can do the same thing for the x direction. Then I will get dx plus or minus v over c times c dt. That one. There you go. And in my example here, I'm assuming that the 2 inertial systems, the blue and the red, are only moving in x direction with respect to each other. And moving in x direction is going to leave the other spatial directions completely unchanged. So dy prime is simply dy, and the z prime is simply dz. So again, not writing down something you don't already know. This is the Lorentz transforms, but now written in, well, as a vector, as a 4-vector. But now, notation-wise, we can ask ourselves the following. We had this introduction of this new symbol, the one symbol that takes into account all 4 of these numbers. And we do the same thing with the prime system. So we really have now a dx primed mu. And we also have the dx unprimed mu. And they are related to each other. That's what the Lorentz transforms tell you, that you can turn one of them into the other. You can ask yourself now, well, how in this new notation should one be turned into the other. In the old notation, just Lorentz transforms, that will be something like this. But can we also write it in terms of this, well, this notation where you have one symbol, the Greek letters, etc., that combine all four of them? And yes, that can be done. Again, let me color code this. If this is a vector in the sense 4 numbers, and this is a vector in the sense of 4 numbers, how do you turn a block of 4 numbers into another block of 4 numbers? You have to put a matrix in between. So there is a matrix that transforms the unprimed into the primed, and that matrix we specify by, well, the capital letter L in Greek. The L stands for Lorentz because this guy is what you call the Lorentz matrix. And you can already read off, if you look at this guy over here, what that Lorentz matrix should look like. Because if I were to write this in terms of a matrix, then you can easily check for yourself that that matrix looks like this, where the original coordinate system, the original 4 vector is the unprimed is on the other side. If you don't believe me, multiply by linear algebra out this matrix times that guy, and you will get this, which is indeed the primed system. So what we can do is take this matrix, that simply is another way of writing down the Lorentz transforms, and condense this whole matrix. I should actually write it in black for my consistent color coding, and just squeeze it all into this object here, the Lorentz matrix, into one symbol. Remember, the nice thing about 4 vectors is that it is also economic. You don't need to write as much. Here you have to write down 16 numbers. But instead, we like to write it all as one big symbol. Well, how do we do this? With the Greek letters again. Remember, one Greek letter that we had over here simply meant which of those 4 numbers do you mean. 0 meant this one, 1 meant that one, 2 meant that one, and 3 meant that one. But now I don't have 4 numbers, I have 4 times 4 numbers, because I have 4 numbers down and I have 4 numbers as a row, so column and row. So I'm not going to need one Greek letter to label where in the column I am. I'm also going to need another Greek letter telling me which of the rows I mean. So the Lorentz matrix in this particular notation has actually 2 Greek indices. The one on top, mu, that says which of the rows do you mean? Do you mean this, 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 or that? And it has another Greek letter. Well, mu is already in use, so we typically take the next Greek letter, which is the Greek letter N, nu. And this tells you which of the columns you're in. So for instance, if this mu is 0 and nu is 0, I mean the 0th row in the 0th column, which is this guy over here, gamma. If I were to say mu is 2 and nu is 0, then I mean the 0, 1, 2 row, 0, 1, 2 row, so I'm here. And then what did I say? It was mu is 2 and nu is 0. Okay, that means this one. So that's the number 0. So on and so forth. So in this symbol, I've encapsulated by choice of my 2 Greek indices which of those 16 numbers I mean. And in doing so, the object that I'm left with, this equation, is all of the Lorentz transforms written in only one single line. So that's the economic part, so to say, of the 4 vector notation. There you go. And well, professional relativists never write this stuff down. They write everything in terms of this. You might notice now, by the way, that there's a Greek index down here and the same Greek index down up there. Again, that's notation. It means please perform a matrix multiplication. If you know your linear algebra, then you know that if you want to have this number, the 0th number, right, this one all the way over here, the upper number, you have to take the upper row and then multiply it with each and every one of those numbers here. So you have to take that one times that one times that one times that, and that one times that. That's what matrix multiplication is in linear algebra. Well, that's what it says here. You have a Greek letter nu and another Greek letter nu, and notation-wise, we simply mean that you have to do matrix multiplication that when you want to be in the 0th row, so that's over here, you want to have this number, that you have to take this row and then let the nus, that's the columns, run from the 0th value to that value, to that value, to that value, and then add everything together. So a Greek index down and a Greek index up simply is shorthand notation for saying do a matrix multiplication. Take those 4 numbers, multiply each individually by those 4 numbers, and add everything together, as the algebra tells you that the matrix multiplication is. So this particular combination is just a shorthand for matrix multiplication, and in this context we call it a contraction. Don't worry about the words, there's nothing new there. Again, it's just matrix multiplication, but written in 4 factor notation with the up index and the down index. We call this a contraction. So the next time that you do a calculation or you read an article and you see a down index and an up index, it is shorthand for let those Greek down and up indices have all of their 4 values. Write it all out and then add everything together. Do a matrix multiplication. A contraction, as we call this. Again, with all of that in mind, this is an extremely economic, short way of writing down everything that we already have on the board. And just to drive the point home, this is 4 equations, because every mu value means one of these 4. So you already write down 4 equations. But because of the contraction, or if you will, the matrix multiplication, the nus also take 4 values. So this splits up into something plus something plus something plus something, 4 terms. So this is shorthand for 4 equations, each and every single one of them having 4 thingies added together. So it's really a whole bunch of equations all grouped into one nice small expression. Okay. Well, everything we've done so far is, well, again, nothing new. There's no new physics. It's just all notation that you might have to get used to for a little bit. But it is the notation that's used everywhere because of the economic structure. But we've only done this for one particular 4 vector, namely sort of the mother 4 vector, time and position. These thingies over there. But if you remember from the beginning what a 4 vector is, it's a block of numbers that obeys a special transformation property, a symmetry. Which one? This one. That it obeys this rule. But time and space are not the only 4 numbers that obey this rule. That sure, individually they might be different, but their combination, this combination stays the same between inertial systems. There are many other examples as well. One quick way of getting a different 4 vector is taking a 4 vector you already know and multiplying it by numbers that you know are themselves invariant. You have to parse this for a moment. If you know that this object is a 4 vector and you multiply it with a number that you know is the same in all inertial systems, then the resulting object will still obey this rule. Listen, I cannot multiply this whole object with the number x, for instance. Why not? Well, because x gets Lorentz contracted from one frame to the other and things become very complicated. Yes? Then from here to here will not be the same. But if I multiply this equation or this 4 vector by, I don't know, the number c, the speed of light, well, the speed of light is the same. It survives the equality sign. It's the same on both sides. So I can very easily do a 4 vector multiplied with a c or divided by c or multiplied with c to the power 17, and the rule would still apply. The 4 vector would be different because now you've multiplied it with c to the 17, but this rule has stayed the same. And obeying that rule is enough to call it a 4 vector. So in this way you can play around, you can get other 4 vectors. So let's do an example, just for funsies. You could, for instance, multiply this whole object with, again, you can do a C, but another object that stays the same in all inertial systems is the mass of an object. So if I were to multiply this whole thing, let's take the green marker, excuse me, the blue one, I can multiply the whole thing with m, because the amount of kilograms is the same in all inertial systems. So that works. This is still a 4 vector, a different one. It's not time and space anymore. It's now time and space times m, but it is a 4 vector. Here's another example. The proper time has the same value in all inertial systems. So if I want, I can divide every single one of these entries by the proper time, because proper time also survives this rule. And now I really have a very different 4 vector, 4 completely different numbers than what I started with, but still obeying that rule. So this combination is again a 4 vector by mathematical definition. And 4 vectors, as you now know, you write with a symbol and a Greek index. The Greek index is again mu. The symbol we actually call P for momentum. Because, and I'm not showing this now, you have to accept this from me, that's because the spatial parts, m dx divided by d tau, and m dy divided by d tau, and m dz divided by d tau, actually are the momentum of a flying particle. You can really sort of see it, because dx dt, d tau, is, well, it's a velocity, times m, that's a kilogram times a velocity. Well, in classical physics is what you call a momentum. There's a slight nuance, because typically in classical physics, non-relativistic, you would not divide by tau, but by t. There's a nuance there. But we still call this momentum. So these 3 entries below are called the momentum, and since for momentum we have the symbol P, we call that whole object P, and the mu then counts, again as before, which of those 4 numbers you mean. You might wonder at this point, okay, well, mu0 is the upper part, and that's a dt and a d tau, and another m and a c. Well, it's not a momentum, right? For momentum you need a velocity, a distance traveled in a certain amount of time, times a kilogram, and this is a different thing. It's the energy. I'm not showing you this, I mean, I'm simply telling you, it's the energy of the particle that's flying about. So with playing around a little, we have now found from the sort of the original 4 vector of duration and distance, we have now found that there's yet another 4 vector consisting of the energy and the 3 momenta together. What also is true is that since we are using the same transformation property, therefore it's a 4 vector, that means that this conclusion is also still true, but now for this new 4 vector P. So the energy momentum 4 vector P mu in the prime system is given by the energy momentum in the unprimed system with the exact same Lorentz transform in between. So there you go, you have an extra rule now. You now have a rule by which you can transform energy and momenta from one inertial system to the other, and all of that written in one go with the exact same Lorentz matrix in between. So in this way we can construct a whole bunch of rules of how particular numbers in one frame transform particular numbers in the other. We can play this as much as we want. If you, well, there's too many examples. Every time again that you multiply these entries with some number that survives this transformation, the result is a 4 vector, and that means it plays by the exact same rule, and you know exactly how those numbers from one frame to another inertial frame change. So it's not just economics that we use 4 vectors, it allows us to construct from a known law of nature a new law of nature. We went from a space and time relationship to an energy momentum relationship. I will mention one more, it's a slightly more advanced example, and again I'm just naming that it is true. There's a very special 4-vector that comes from electromagnetism, namely phi, the electrostatic potential, right? It's sort of the energy that two particles feel when they attract each other or repulse each other electromagnetically. But if you know your electrodynamics, then you know that there is also this thing that we call the vector potential. It's a potential energy that tells you, it's called A, it has an X, Y, and Z direction, and it also tells you how much electromagnetic field there is. So instead of writing down how particles and charges feel each other by electric fields and magnetic fields, you can also write them in terms of the electrostatic potential and what is called the vector potential. Why this is true is a nice course in electromagnetism, but it is factually correct. So instead of saying I have an electric field in 3 directions, that's 3 numbers, and a magnetic field in 3 directions, that's another 3 numbers, 6 numbers total, electromagnetism teaches you that you can also write down the same information in only 4 numbers, these 4 numbers. And lo and behold, those 4 numbers again play by exactly this rule. You have to show this, that's an exercise to do that. But I'm simply telling you now that they do. And since, if you now know that the vector potential, these 3, and the scalar potential work, form a 4-vector, that means they too obey this rule. And now you know how electric and magnetic fields change from one frame to the other. And all of that using all this beautiful language. So this particular one, again, is written because it's a 4-vector, because it plays with this rule. It's also given with the Greek index. And the Greek index, again, we call mu. And the object itself is named after these 3. It's called the, it's called the Maxwell field, because it's named after Maxwell. So, the Maxwell field is simply given by, in a primed frame, is given by how it looks in the unprimed frame, and then matrix multiplied by, yet again, the Lorentz tensor that we had before. Alright, so all of this, very little new information, simply rewriting what we already knew beautifully in terms of 4 vectors. To finalize, I will say one more thing, because you might see this very often in articles. Because up until this point we have been writing our 4 vectors with an index up. So let's write down a 4 vector. I'm not specifying what it is. Let's call it 4 vector B with Greek index mu, so it's 4 numbers. And up until this point, every one of our 4 vectors had an index up. In nomenclature, this is called a contravariant 4-vector. Don't worry about the naming, it's just names. But every now and then, you might open up an article and you might find a 4-vector with an index down. That's what is called a covariant 4-vector. Covariant, contravariant, up until to this point, it simply means is the index up or down. And those are not the same objects. They might specify the same physics, as in this might be energy momentum and this energy momentum, but with a slight difference. And just for completeness, in case you find this in the wild, reading articles or doing a different course, let me tell you what the connection is between them. Suppose that somebody gives you a contravariant 4-vector, so that's B with an index up, and you're really interested in getting its corresponding covariant 4-vector, that means with the index down. Then you have to do a matrix multiplication. There is a particular matrix that turns contravariance into covariance. And that very particular matrix that does it for you has its own name. It's called eta. the Greek letter eta. And again, just like the Lorentz matrix, it has two indices because you have to keep track of not just the rows as you would in a vector, but also the columns. So you need one index that counts the rows and one index that counts the columns. 16 numbers in total, two Greek letters. And again, notation wise, the fact that you have an index down and an index up means you do a matrix multiplication. That's by simply by definition of notation, as we did here too. Now what does it look like? The special matrix that transforms contravariance into covariance by matrix multiplication, denoted by double index, is minus c squared 1, 1, 1. And if you think, well, I don't know why this is true, this is simply definitionally so. It's simply defined this way. This matrix is defined such, or I should say differently, the covariant 4-vector, the index down 4-vector, is simply defined as the contravariant one, index up, matrix multiplied by this particular matrix. Simply definitional. So by this matrix, if you want, in this way that I'm explaining it now, it's simply a transformation between contra to covariant. And you might wonder, well, okay, but why would you define something like this? It's because our original Minkowski line element can now be written in a very beautiful and nice, succinct way. By the way, for completeness, this particular matrix is called the Minkowski matrix. And if you squint, you can see why. Because the Minkowski line element tells you that you have to take the t part, the 0 part of a 4-vector, and multiply it by minus c squared. Hey, look, that's this one. And it also says that you have to take the spatial parts and multiply it with the number 1. That's these ones over here. And every other combination should not appear at all, which means they are multiplied by the number 0. Those are all these zeros over there. So if you squint, you can already see that this minus c squared and the plus 1 and the plus 1 and the plus 1 there are just collected here in this Minkowski matrix. Well, this observation is enough to show you that the Minkowski line element can also be written in a nice 4-vector notation. So I'm going to combine everything together now. That if you take the Minkowski line element, the Minkowski matrix, and you take the position 4-vector, the one that started with c dt, dx, dy, dz, but you matrix multiply it twice, look, Greek index up and down, that means matrix multiplication here, but now I have two of them. If you do this matrix multiplication, it simply means take the 0, 0 part of the two 4-vectors, that was c dt. Well, they're multiplied, that gives you dt squared. Multiply it with this guy's 0, 0 part, is minus c squared. You're going to get exactly that. But matrix multiplication says you also have to take all the other terms, right? It becomes a sum of things. It also says that you have to take the mu1, nu1 combination and multiply it with its Minkowski matrix entry. Well, dx1 and dx1 is what you call the amount of distance in x direction, dx squared. And you have to multiply it with the Minkowski matrix entry at the 1, 1 position, which is 1. So you will get plus dx squared. And continuing this way, you also get dy squared and dz squared. In other words, this combination is just another, it can just be written in 4-vector notation as this, right here. This is exactly that. That's why it's called the Minkowski matrix. Now the other side, because we know that this is invariant, right? That's the symmetry on which everything is based, that Minkowski line element looks the same on both sides, means that in the primed coordinates, note prime, it's the same thingy over there. Yes? So what I've written here now is just the Minkowski line element, but now written in terms of 4 vectors with all the Greek indices using this particular Minkowski matrix. This rule that you know from special relativity is just that rule, but now in this 4 vector notation. And to finalize, with everything combined together, we can do something very, very beautiful. Because this is not just true for the x 4 vectors. We were having this whole story that this particular combination is also true for all kinds of other factors. For instance, energy momentum, but also the one from electromagnetism with the scalar potential and the vector potential. So this rule is also true if this was any random other 4 vector A, as long as it's a 4 vector, and any random 4 vector B, as long as it's a 4 vector, then this is still true. This is still a true statement. Remember, you can create a 4 vector A and B from the 4 vector for x and t just by multiplying it with things that themselves are invariant, like the mass or the speed of light or the Minkowski line element itself. So knowing that that's the case, I can turn my Minkowski line element written in this particular 4 vector notation into one that contains any 2 4 vectors A and B. And now we found something beautiful, because look, it's still invariant. So if you have a 4 vector A, and you know its numbers in coordinate system A, in the on-prime coordinate system, and you also in that on-prime coordinate system you have a 4 vector B, and you know its numbers in that on-prime coordinate system, then this particular combination is going to be the same in any other coordinate system. So A is not the same as A primed, B is not the same as B primed, but this combination is always the same. So we've done something very beautiful here. We've taken an invariant, some combination that we know is always going to be the same in every coordinate system, and turned into a statement how you can create all kinds of other invariants. Other numbers that you know that will stay the same. These numbers. Notation wise, you might actually see the following, that if you only look at the first part over here, you have an index up, contravariant, Minkowski tensor, then according to this rule, that's the same as you would have had the dA covariant with the index down. So the same rule written slightly different, using the Minkowski tensor to bring a contravariant into a covariant, and do this on both sides, then you see the following. There you go. Again, it's still the same rule, it's just using the notation with index down, because that's what the Minkowski tensor does. It brings the index down by definition. So this is the way that one typically encounters this in all kinds of articles. And that's what I'm going to end up with in my story now. In many articles of physics, for instance particle physics or theoretical physics, you will find that people construct expressions that look like this. A covariant tensor, matrix multiplied with a contravariant. Contravariant matrix multiplied with a covariant. Because this story tells you that sure, this 4 vector is not the same as its primed version, and this 4 vector is not the same as its primed version, but this particular combination is always the same. It's an invariant. And if you are a physicist, particle physicist, theoretical physicist, what have you, if you want to construct a theory of nature, but you don't want the theory only to hold in one inertial system, but in all inertial systems, you better look for invariants. It's good if you write your theory in terms of something that you know is the same in the primed and the unprimed system. Because then you can be certain that your theory, whatever it is, will have the same rules in all inertial systems. This is what you call the principle of relativity. You want your physics to be the same in all inertial systems. And with this bag of tricks, we have found how to construct these invariants. Take a 4 vector, A, make it covariant, means index down. Matrix multiply it with any other 4 vector, B, index up. Then this construct is always invariant. So, open up a textbook on particle physics or theoretical physics, and you will see that almost all expressions are written as matrix multiplications of co- and contravariance vectors, exactly for that reason, because they want to uphold the principle of relativity and get the same values in all inertial systems. All of that simply from changing a little bit of notation. Steep learning curve, but it's not just economics that you can write a whole bunch of equations in very short amount of space. No, it gives you new rules of physics. Before we had a whole list of new 4 vectors, but now you know that once you have your 4 vectors and you take a co and a contra and you put them together, you get an invariant and your theory holds in all coordinate systems. That is why it's important. It's not just economics, shorthand writing. It teaches you how to create theories of physics that are the same in all inertial systems. So, don't be surprised in your different courses or the books that you open that every object that they work with are of this particular